Somme, France, July 1st, 1916. General Fritz von Below peers through the periscope of his German trench as British artillery hammers the defensive lines for a fifth consecutive day. He knows this pattern: heavy bombardment, then silence, then vulnerable infantry advancing through the mud. He has seen the British repeat this mistake dozens of times. His machine guns are ready, the bunkers intact beneath meters of reinforced concrete. But at 7:30 in the morning, something changes. The fire does not stop. The explosions move forward like a living wave, a wall of steel walking eastward alongside the British infantry. Von Below grabs the field telephone with a trembling hand. "Unmöglich," he whispers. "Impossible." For the first time in modern warfare history, artillery does not precede the attack. It accompanies it, protects it, guides it meter by meter across no man's land. Welcome. Today you will discover how a single tactical innovation transformed artillery from a static destruction instrument into a mobile surgical scalpel, capable of coordinating thousands of guns with clockwork precision. By the end of this episode, you will understand why the creeping barrage represented for German generals a shock as profound as the introduction of gas or the tank, and how this technique literally saved hundreds of thousands of Allied lives by transforming the paradigm of infantry assault. We will see the exact numbers, how losses dropped from 75% in traditional attacks to 32% with coordinated barrage, figures extracted from the operational records of the British Expeditionary Force preserved in the National Archives at Kew. We will explore the hidden mathematics behind this deadly dance between shells and men, where every second of delay or anticipation meant the difference between protection and massacre. The Great War of 14 to 18 is often reduced in collective imagination to a static image: trenches, mud, suicidal assaults. But this simplification conceals an unprecedented scientific and industrial revolution. When the conflict erupted in August 1914, European armies still operated according to Napoleonic doctrines, updated only superficially. Artillery served to bombard fortifications, to terrorize the enemy before assault, to create breaches in defenses. No one had foreseen what would happen when repeating rifles, machine guns, and barbed wire transformed every meter of open ground into a death zone. The first battles of the Western Front brutally revealed the obsolescence of traditional tactics. At the Marne, at Ypres, at Neuve-Chapelle, frontal attacks transformed into calculable massacres. For every 100 meters conquered, thousands have fallen. The problem was mathematical before it was strategic. A heavy artillery shell takes approximately 25 seconds to cover 10 kilometers from the moment of firing. An infantry soldier loaded with 20 kilos of equipment crosses 70 meters of no man's land in about 2 minutes walking fast, 1 minute 20 running. But the real conditions of mud, barbed wire, and enemy fire tripled these times. Artillerymen had to cease fire at least 5 minutes before infantry reached enemy lines to avoid hitting their own men. These 5 minutes were sufficient for German defenders to exit bunkers, position machine guns, and exterminate the attackers. British reports from 1915 document losses of 62 to 84% of personnel engaged in assaults preceded by conventional bombardment. The British Third Corps lost 12,400 men in 3 days at Loos, gaining 300 meters. The mathematics was merciless, and the generals knew it. The theoretical solution was simple to state, but monstrously complex to implement. Synchronize the movement of artillery with that of infantry, creating a mobile curtain of explosions that preceded the attackers by just 50 to 100 meters. Close enough to keep defenders in bunkers, far enough not to pulverize one's own soldiers. But transforming this idea into operational reality required simultaneously solving problems of communication, ballistic calculation, industrial production, and human coordination on a scale never before attempted in military history. The first obstacle was standardization. Allied armies in 1915 used dozens of different cannon models: British 114mm howitzers, Mark I and Mark II, French 75mm guns, model 1897, heavy 149mm howitzers, requisitioned and modified naval pieces. Even obsolete cannons from the 1880s returned to service. Each model had different projectile velocity, trajectory, range, and rate of fire. Creating a coordinated barrage meant calculating separate firing tables for each weapon type, considering air temperature, humidity, wind, barrel wear, propellant variations. The Royal Artillery established specialized calculation units in early 1916. These were not traditional gunners, but mathematicians, surveyors, engineers, recruited from universities and technical schools. Captain Henry Tizard, later scientific advisor to the British government, spent 4 months at Woolwich Arsenal, developing what he called predicted fire tables. The process was obsessively detailed. Each gun battery received a reference book of 300 pages containing corrections for every conceivable variable. Temperature above 15 degrees Celsius. Add 2 degrees of elevation for every 1,000 meters of range. Barrel fired more than 200 rounds. Subtract 1 degree. Wind from the west at 15 kilometers per hour. Adjust aim point 23 meters right. These calculations assumed perfect information, which of course never existed on the battlefield. Communication represented an even greater challenge. Coordinating a creeping barrage required precise synchronization between hundreds of gun batteries spread across dozens of kilometers and infantry units advancing under fire. In 1914, battlefield communication relied primarily on runners, men who literally sprinted through artillery fire, carrying written messages. The average survival time of a runner during major offensives was estimated at 48 hours. Field telephones offered an alternative, but cable-laying crews suffered even higher casualties, and a single shell could sever lines connecting entire divisions. Wireless radio technology existed, but was primitive. Equipment weighed over 50 kilos, required 2 operators and a separate power generator, had range limited to 5 kilometers in ideal conditions, and was vulnerable to atmospheric interference. The British solution combined old and new methods with ruthless pragmatism. For the initial barrage plan, everything was calculated in advance and distributed as written orders days before the attack. Each battery commander received a schedule specifying exact firing times, ranges, and shell types minute by minute. A typical creeping barrage order for a single battery looked like this: 7:30 hours, range 4,200 meters, high explosive, 4 rounds per minute. 7:33 hours, range 4,300 meters, continue fire. 7:36 hours, range 4,400 meters, continue fire. This continued for hours. The entire sequence was rehearsed repeatedly behind the lines with dummy ammunition, but rehearsal could not account for battlefield chaos. What happened if infantry encountered unexpected resistance and fell behind schedule? What if German counterfire destroyed key batteries? The answer was a system called lifts that combined rigid timing with limited flexibility. The barrage advanced in predetermined increments, typically 100 meters every 3 to 4 minutes, regardless of infantry progress. Officers carried synchronized watches set to Greenwich Mean Time, distributed in waterproof cases days before the attack. These watches were manufactured specifically for military use by companies like Waltham and Omega, produced in quantities of tens of thousands. Losing one's watch could result in court-martial, as the entire system depended on temporal synchronization more precise than anything previously attempted in warfare. Artillery production had to scale exponentially to make creeping barrage practical. A single divisional attack covering 2 kilometers of front and advancing 1 kilometer deep required approximately 40 to 60 artillery batteries, each firing continuously for 30 to 90 minutes. Each gun fired between 100 and 300 shells during a typical barrage. This meant a single attack consumed 15,000 to 50,000 artillery shells. The Battle of the Somme, which began July 1, 1916, saw British forces fire over 1,700,000 shells in the preliminary bombardment alone, then continued firing at reduced but still massive rates for 4 months. Annual British shell production increased from 500,000 shells in 1914 to 76 million in 1917, a 150-fold increase in 3 years. This production miracle required transforming civilian industry. British munitions factories in 1916 employed over 900,000 workers, of whom 65% were women. The Chilwell shell filling factory in Nottinghamshire alone produced 19 million shells during the war. Workers filled shells with explosives in assembly line fashion, each person performing one specialized task, repeated thousands of times per shift. The work was extraordinarily dangerous. At Chilwell on July 8, 1918, an explosion killed 134 workers and injured another 250. Similar disasters occurred at Silvertown in 1917, at a French factory in Rouen, at dozens of smaller facilities. The industrial production of death extracted its own toll before shells ever reached the front. Quality control became obsessive because a single defective shell could destroy an entire barrage plan. If one gun in a battery fired a dud or a short round, it created a gap in the protective curtain that German machine gunners could exploit. British ordnance inspectors developed standardized testing protocols. 5% of shells from each production batch were randomly selected and test-fired at proving grounds. Propellant batches were analyzed chemically to ensure consistent burning rates. Fuse mechanisms were tested in climate chambers simulating battlefield conditions. Despite these efforts, DYAD rates remained between 5 and 15%, depending on shell type and manufacturer. Artillerymen learned to calculate effective coverage rather than total shells fired, assuming roughly 10% would fail to detonate. The first true test of coordinated creeping barrage came not at the Somme, as popular history often suggests, but during smaller-scale attacks in late 1915 and early 1916. The British Fourth Army conducted experimental barrages at Loos in September 1915, though the results were mixed due to inadequate preparation and insufficient artillery density. It was at Vimy Ridge in April 1917 where the technique achieved its first unambiguous success, demonstrating to German defenders that the rules of trench warfare had fundamentally changed. Vimy Ridge represented everything difficult about Western Front warfare, compressed into 7 kilometers. The ridge dominated the surrounding landscape, rising 60 meters above the Douai plain, offering German observers perfect visibility over Allied positions for kilometers in every direction. The Germans had held Vimy since October 1914 and had transformed it into a fortress. 3 defensive lines stretched across the ridge, each protected by deep dugouts capable of sheltering entire battalions 30 meters underground. The French had attempted to take Vimy twice, in May and September 1915, suffering over 150,000 casualties with nothing to show for it. British and Canadian commanders planning the April 1917 assault understood they faced not just a tactical challenge, but a proving ground for modern offensive warfare. The artillery plan for Vimy was unprecedented in scale and precision. General Arthur Currie, commanding the Canadian Corps, assembled 983 guns along the 7-kilometer front. This density of 1 gun every 7 meters represented the highest concentration of artillery yet achieved in the war. More importantly, the guns were organized into a sophisticated coordination system. Heavy guns, primarily 149mm and 8-inch howitzers, would suppress German artillery positions and destroy deep dugouts. Medium guns would cut barbed wire and destroy machine gun nests. Light field guns, the 75mm and 18-pounders, would create the actual creeping barrage, advancing ahead of infantry. The preparation took weeks and revealed the obsessive attention to detail required for success. Survey teams mapped every German position using aerial photography, a technology barely 5 years old. The Royal Flying Corps flew over 12,000 reconnaissance missions during the preparatory phase, producing detailed topographic maps accurate to within 5 meters. Artillery officers studied these maps using a new technique called calibration, where each gun was individually tested to determine its unique ballistic characteristics. 2 guns of identical manufacture could have slightly different ranges due to microscopic variations in barrel dimensions or propellant chemistry. Calibration involved firing test shots at known targets and measuring the exact point of impact, then calculating corrections for each individual weapon. Ammunition stockpiling represented a logistical nightmare solved through brute force and railway engineering. The attack required 2,700,000 shells pre-positioned within range of the target. This mass of metal and explosive weighed approximately 50,000 tons, equivalent to loading and unloading 62 freight trains. The British built 30 kilometers of new light railway track behind the lines specifically to supply the guns at Vimy. Ammunition dumps were camouflaged with nets and dispersed to prevent German counter-battery fire from triggering catastrophic explosions. Each battery position had shells stacked in precise arrangements, allowing rapid reloading, often with wooden frameworks holding shells at waist height so loaders did not have to bend between shots. The preliminary bombardment began March 20th, 1917, 2 weeks before the infantry assault. This was not the creeping barrage, but rather systematic destruction of German positions. Counter-battery fire targeted German artillery using sound ranging and flash spotting, new technologies that triangulated enemy gun positions by detecting either the sound waves or muzzle flash of firing. British guns destroyed or silenced 83% of German artillery before the main attack, a critical prerequisite for the creeping barrage to succeed. If German guns could fire on advancing Allied infantry, the entire coordination would collapse into chaos. Wire cutting consumed thousands of shells. German barbed wire defenses at Vimy were extraordinary. Some sections 15 meters deep with wire strands as thick as a man's thumb. High explosive shells cut wire through blast effect, but required precise fusing to detonate at exactly the right height above ground. Fuses set too long allowed shells to bury themselves before exploding, wasting energy in the earth. Fuses set too short caused air bursts that scattered wire without cutting it. British fuse specialists experimented with Gray's fuses, designed to detonate on first contact, and instantaneous fuses using super-sensitive mechanisms. Even with optimal fusing, cutting wire completely required approximately 3 shells per meter of front, meaning 40,000 shells just for wire cutting along the 7-kilometer assault zone. The morning of April 9th dawned cold with sleet falling as Canadian infantry climbed out of their trenches at 5:30. The creeping barrage began precisely at that moment, a wall of explosions 100 meters ahead of the front line. The noise was described by survivors as physically painful, a continuous roar that made thought impossible. Private Donald Fraser of the 31st Battalion wrote in his diary, "The ground shook continuously. I could feel the shock waves from shells passing overhead, compression and decompression beating against my chest. Speech was impossible. We moved forward in a daze, following the shell bursts by instinct rather than sight through the smoke and sleet. The barrage advanced at a rate of 100 meters every 3 minutes for the first phase, covering the first 500 meters to the German front trench line. Artillery planners had calculated that Canadian infantry, moving through destroyed ground and scattered resistance, could maintain a pace of approximately 30 meters per minute. The 3-minute lift schedule provided a 30-meter safety margin, enough to prevent friendly fire casualties while keeping Germans suppressed until the moment of assault. This mathematics of death proved remarkably accurate. Canadian casualties in the first wave were roughly 30%, horrific by civilian standards, but dramatically lower than the 70 to 80% losses typical of conventional attacks. The coordination held despite battlefield chaos. At certain points, German strongpoints halted Canadian advances. Companies found themselves pinned down by machine gun fire, unable to advance with the barrage. The rigid timing meant the protective curtain moved forward regardless, potentially leaving infantry exposed. But Canadian officers had trained for this contingency. Junior officers and sergeants carried detailed maps showing the barrage schedule. When their men fell behind, they ordered troops to wait in shell holes until the next lift brought the barrage forward another 100 meters, then timed their advance to reach German positions just as the shells moved on. This flexibility within a rigid system represented sophisticated tactical thinking, treating the barrage as a series of opportunities rather than a single coordinated rush. German defenders experienced the creeping barrage as psychological warfare as much as physical destruction. Lieutenant Heinrich Bauer of the 79th Reserve Infantry Regiment wrote after his capture, "We heard the bombardment for days, always in the distance, destroying positions behind us. Then on the 9th, it came closer. We knew the moment. We ran from the dugout to man positions, and the shells were everywhere. Not random, not scattered, but a curtain moving toward us, methodical, inevitable. We fired our machine guns blindly into the smoke, hoping to hit something. Then the shells moved past us, and we thought we had survived. But Canadians were already in the trench, among us before we understood. The shells had not destroyed our position, but had imprisoned us in the dugout until too late. This testimony reveals the psychological innovation of creeping barrage. Previous bombardments aimed to destroy, to reduce defenses to rubble. The creeping barrage aimed to suppress, to keep defenders unable to fight until the moment they were overrun. German soldiers at Vimy were often physically unharmed, their weapons functional, their positions intact, yet they surrendered by the thousands because the barrage had prevented them from organizing resistance at the critical moment. The Canadian Corps captured 4,000 German prisoners on April 9th, the largest single-day haul yet achieved by any Allied force on the Western Front. By noon on April 9th, the Canadians had captured the first 3 German defensive lines and held most of the ridge. The advance covered 3.5 kilometers in some sectors, an achievement that would have been unthinkable without the creeping barrage. Total Canadian casualties for the 4-day battle were 10,600, severe but far below the 150,000 French casualties for similar objectives 2 years earlier. The kill ratio had shifted dramatically. For every Canadian killed, approximately 2 Germans died and another 2 were captured, whereas previous attacks saw attackers suffer 3 to 5 times defender casualties. The German military establishment did not immediately grasp the full implications of Vimy Ridge. Initial reports from the front attributed the defeat to local factors: inadequate reserves, poor communication, exhaustion of front-line troops. But as similar defeats accumulated through spring and summer 1917, at Arras, at Messines, at Passchendaele, German High Command recognized they faced a systematic problem requiring systematic response. The creeping barrage had broken the fundamental equation that made trench defense viable. Crown Prince Rupprecht of Bavaria, commanding the 6th Army in Flanders, wrote in his diary on May 10, 1917, "The British have perfected a method that renders our defensive doctrine obsolete. Our men cannot reach firing positions before enemy infantry arrives. We remain underground like rats, helpless, waiting to be killed or captured. Yesterday at Messines, we lost an entire regiment, not destroyed, but captured intact in their dugouts. The old methods of defense have failed." This admission from one of Germany's most respected field commanders revealed the crisis facing German military thinking. German tactical doctrine since late 1914 had emphasized elastic defense in depth. The front line was lightly held as a warning position. The main defensive strength lay in a second line 500 to 1,000 meters behind the front, positioned to counterattack any enemy breakthrough. Supporting this was a third line with artillery and reserves 2 to 3 kilometers back. This system worked beautifully against traditional attacks where bombardment preceded assault with a clear gap. German troops in the second line waited out the bombardment in safety, then moved forward to massacre exposed Allied infantry crossing no man's land. The creeping barrage collapsed this timeline by accompanying infantry all the way to the second defensive line, suppressing defenders continuously until overrun. Captured German documents from mid-1917 reveal desperate attempts to counter the new threat. A tactical manual issued by the Second Army in June 1917 advised, "When enemy barrage begins moving forward, defenders must immediately exit shelters and man positions despite ongoing fire. Casualties from remaining under barrage are acceptable compared to certainty of capture if enemy infantry arrives at unmanned positions. Company commanders will enforce this order ruthlessly. This order essentially demanded German soldiers stand exposed to artillery fire, an impossible ask that revealed the dilemma posed by creeping barrage. Men naturally sought shelter from explosions, but shelter meant capture. The psychology of self-preservation fought against tactical necessity. Some German units attempted technical countermeasures. At Passchendaele, in July 1917, German artillery experimented with their own counter-creeping barrage, attempting to place a wall of shells between British infantry and the British barrage, protecting them. The timing required was extraordinarily difficult, essentially threading shells through a moving 50-meter gap while both British barrage and British infantry advanced. German artillery doctrine had not developed the survey and calibration techniques necessary for such precision. The counter-barrage attempts killed some British troops but also inflicted significant friendly fire on German defenders, and the tactic was largely abandoned by August. General Erich Ludendorff, effective commander of all German forces on the Western Front from mid-1916, ordered a comprehensive study of Allied artillery methods in August 1917. The resulting report, Die feindliche Artillerie Taktik, ran to 170 pages and was distributed to all Army and Corps headquarters. The document is preserved in the German Federal Military Archives in Freiburg and provides extraordinary insight into how Germany's military elite understood their predicament. The report's summary stated, "The enemy has achieved coordination of artillery and infantry that transforms offensive operations from gamble to engineering problem. Their methods require resources and technical sophistication we cannot currently match. Our artillery lacks sufficient guns, shells, and trained specialists for equivalent tactics. We must instead reform defensive doctrine to minimize barrage effectiveness." The recommended reforms were radical. German defensive depth increased dramatically. By late 1917, German positions extended 5 to 8 kilometers deep with multiple intermediate lines, compared to the 2 to 3 kilometers typical in 1916. The theory was that even a perfectly executed, creeping barrage could only advance infantry 3 to 4 kilometers before exhaustion and disorganization made further progress impossible. If German defenses extended beyond that range, any Allied success would be temporary and subject to counterattack once the barrage ended. German frontline trenches became less elaborate and more lightly held. Rather than deep dugouts protecting entire battalions, forward positions used smaller shelters for squad-sized groups with orders to delay rather than hold. The Hindenburg Line, constructed during winter 1916-17, embodied this philosophy. The forward zone consisted of outposts designed to be sacrificed, with main defensive positions 3 kilometers behind the nominal front line. When British forces advanced behind creeping barrages against the Hindenburg Line, they often captured the forward zone easily, then found themselves exhausted and exposed when they reached the actual defensive positions beyond artillery support range. Individual German soldiers adapted in various ways, as revealed through letters and diaries examined after the war. Gefreiter Wilhelm Kaisen wrote to his family in September 1917, "We have learned to judge the enemy barrage by sound. When shells fall in steady rhythm, it is the walking fire, and we must run forward immediately toward the enemy, not back. Between our position and the next line of explosions, there is safety for perhaps 2 minutes. In those 2 minutes, we set up the machine gun and fire at anything moving in the smoke. Sometimes we kill many. Sometimes we see nothing, and the enemy is upon us. It is madness, but better than waiting in the dugout for certain capture. This tactic of moving into the barrage represented desperate innovation born from necessity. German soldiers realized the safest place during a creeping barrage was the ground just crossed by the advancing curtain of fire, where shells would not fall again for several minutes. By rushing forward through the smoke and confusion, German defenders could sometimes establish firing positions in the brief gap between barrage and infantry. The tactic required extraordinary courage and often proved suicidal, but it occasionally succeeded in disrupting Allied attacks. German casualties reflected the new reality. Prior to widespread creeping barrage use in early 1917, German losses on the Western Front averaged approximately 20,000 per month during periods of active operations. From April through November 1917, during major Allied offensives employing creeping barrage, German casualties averaged 65,000 per month, more than triple. The ratio of killed and wounded to prisoners shifted dramatically. In 1916, prisoners represented roughly 15% of German casualties. In 1917, prisoners increased to 32%, indicating that German troops were being overrun rather than fighting to exhaustion. The prisoner interrogation reports compiled by British and French intelligence services provide the most direct evidence of German shock and demoralization. A typical report from July 1917 stated, "Prisoner from 220th Division reports his company of 150 men reduced to 23 effectives in 3 days of bombardment. States men remained in dugouts despite orders because emerging meant certain death from shells. British infantry appeared at dugout entrance before any alarm given. Prisoner believes resistance impossible against walking barrage and expects Germany to lose the war unless new methods found. Riprova Claude può commettere errori. Verifica sempre le risposte con attenzione. Sone 4/5. The creeping barrage, as practiced in 1917, ceased to exist as a military technique decades ago, rendered obsolete by mechanization, air power, and precision-guided munitions. Yet its legacy permeates modern military doctrine in ways both obvious and subtle. The fundamental insight that firepower and maneuver must be synchronized rather than sequential underpins every combined arms operation from World War II to contemporary conflicts. The creeping barrage was humanity's first large-scale attempt to create what modern theorists call suppression corridors, protected channels through which forces can advance against prepared defenses. Modern artillery doctrine retains the mathematical precision pioneered by creeping barrage planners. Every Western military uses digital fire control systems that are direct descendants of the manual calculation tables developed at Woolwich Arsenal in 1916. The United States Advanced Field Artillery Tactical Data System, deployed since the 1980s and updated continuously, performs in microseconds calculations that required teams of mathematicians hours to complete a century ago. But the underlying principles remain identical, correcting for temperature, wind, barrel wear, propellant variations, and projectile characteristics to place shells precisely where intended. The GPS-guided Excalibur artillery round, accurate to within 10 meters at 40 kilometers range, represents the technological culmination of the trajectory science forced into rapid development by the demands of creeping barrage. The concept of synchronized watches and precise timing schedules became fundamental to all military operations. Before the Great War, Military time coordination was relatively casual, with units operating on approximate schedules with built-in flexibility. The creeping barrage demonstrated that modern warfare required temporal precision measured in seconds across formations of hundreds of thousands of men. This insight carried forward into every subsequent conflict. The D-Day landings on June 6, 1944 involved coordination more complex than Vimy Ridge, but built on identical principles: predetermined schedules, synchronized watches, and rigid adherence to timetables despite battlefield chaos. Modern military operations use atomic clock synchronized systems accurate to microseconds, but the conceptual framework remains unchanged from 1917. Industrial mobilization for artillery production established precedents that shaped 20th century warfare. The British shell production system, employing nearly 1 million workers by 1918, demonstrated that modern war required converting entire national economies to military production. This lesson was not forgotten. When Germany rearmed in the 1930s, when the United States mobilized for World War II, when the Soviet Union industrialized for the Cold War, planners explicitly studied Great War munitions production as a model. The factory line approach to weapons manufacturing, the statistical quality control systems, the integration of female labor into heavy industry, all trace direct lineage to the shell crisis of 1915-16 and the industrial response it provoked. The psychological impact of creeping barrage influenced infantry tactics permanently. Before its introduction, infantry assault doctrine emphasized speed and elan, getting across no man's land as quickly as possible before defenders could respond. The creeping barrage taught that methodical advance in coordination with fire support produced better results than desperate rushes. This principle evolved into the fire and movement tactics that dominate modern infantry operations. Squad-level tactics today involve one element suppressing enemy positions with sustained fire while another element maneuvers, essentially a micro-scale creeping barrage where rifle and machine gun fire replaces artillery. Training manuals from the United States Marine Corps and British Army explicitly trace this doctrinal evolution from Great War barrage tactics. The development of counter-battery radar and sound-ranging technology during the Great War laid foundations for modern battlefield sensors. The need to locate and destroy German artillery before creeping barrages commenced drove innovation in acoustic triangulation and flash spotting. These primitive sensor systems evolved into the sophisticated radar and signals intelligence networks that dominate contemporary warfare. Modern counter-battery radar can detect incoming artillery shells mid-flight, calculate the firing position, and transmit targeting data to friendly artillery for immediate counterfire, all within 30 seconds. This capability directly descends from the sound-ranging boards operated by British artillery surveyors at Vimy Ridge, where triangulation calculations took 30 minutes and required teams of specialists plotting data on large paper maps. Cultural memory of the creeping barrage exists primarily within military institutions rather than public consciousness. The technique lacks the dramatic visual impact of tanks or aircraft, the technological mystique of submarines or poison gas. Yet within artillery communities across Western militaries, the creeping barrage occupies a revered position. The Royal Regiment of Artillery maintains detailed archives of barrage planning documents from major Great War battles. Officer candidates study Vimy Ridge as a case study in coordination and planning. The United States Field Artillery School at Fort Sill, Oklahoma, includes Great War barrage techniques in its historical curriculum. using them to illustrate principles of massed fires and synchronization that remain relevant despite technological transformation. Academic military history has increasingly recognized the creeping barrage as a pivotal innovation. Historians, including Paddy Griffith, Robin Pryor, and Trevor Wilson, have argued convincingly that Allied forces learned to conduct effective offensive operations by late 1917, contradicting the older narrative of incompetent generals sending men to pointless death throughout the war. The creeping barrage stands as primary evidence for this revisionist interpretation. When properly resourced and executed, as at Vimy Ridge, Messines, and Cambrai, creeping barrages enabled significant advances with manageable casualties. The tragedy was not that Allied commanders learned nothing, but that they learned too slowly, and the lessons came at horrific cost. The technique also influenced post-war military thought in unexpected ways. German theorists studying their 1917 defeats concluded that static defense was obsolete and future warfare must emphasize mobility and maneuver. This thinking contributed directly to the development of blitzkrieg doctrine in the 1930s, where rapid mechanized advances aimed to bypass enemy strong points rather than reduce them with firepower. The German approach in World War II represented an inversion of creeping barrage philosophy. Instead of using firepower to enable infantry advance, use mobility to make firepower concentration irrelevant. The dialectic between these approaches, firepower-centric versus maneuver-centric warfare, continues to shape military doctrine today. Contemporary artillery employment in conflicts from Iraq to Ukraine shows both continuity and evolution from creeping barrage principles. Modern armies no longer use literal creeping barrages, but they do employ suppression programs where artillery fire is scheduled to keep enemy forces unable to effectively resist while friendly maneuver forces advance. The timing is looser, the coordination more flexible, but the core concept endures. Video footage from Ukrainian forces conducting counteroffensives in 2022 and 2023 shows artillery fire systematically advancing ahead of mechanized units, a recognizable descendant of techniques perfected at Vimy Ridge despite the century separating them. The creeping barrage represents one of those rare historical moments where tactical innovation, industrial capability, and operational necessity converged to permanently transform warfare. What began as a desperate attempt to solve the stalemate of trench warfare became a template for coordinating complex operations across time and space. The German generals who watched in shock as Allied barrages walked across their defenses in 1917 were witnessing the birth of modern combined arms warfare, even if they could not fully articulate what they were seeing. The numbers tell the story with brutal clarity. At Loos, in September 1915, before effective creeping barrage techniques, British forces suffered 60,000 casualties to advance 4 kilometers. At Vimy Ridge, 18 months later, Canadian forces suffered 10,000 casualties to advance the same distance and actually held the ground captured. The difference was not courage or determination, qualities soldiers on both sides possessed in terrible abundance, but rather the application of scientific method to the problem of assault. Mathematics, engineering, and industrial production combined to create a tactical system that, while still horrifically lethal, at least offered attackers a reasonable chance of success rather than near certain death. Understanding the creeping barrage illuminates broader truths about military innovation. Technological advantage alone is insufficient. The Great War began with all armies possessing similar weapons and ended with similar weapons but vastly different capabilities. The difference lay in doctrine, training, and coordination. The British Army that executed the Vimy barrage bore little resemblance organisationally to the British Army of 1914, despite wearing the same uniforms and carrying similar rifles. The transformation occurred in communication systems, planning processes, specialist training, and most importantly, in the intellectual framework officers used to conceptualize operations. For modern audiences, the creeping barrage offers lessons beyond military history. Any complex system requiring coordination of multiple specialized components under time pressure faces analogous challenges. The solutions developed by Great War artillery planners, standardization, rigorous testing, redundant communications, detailed planning with flexibility for execution remain relevant across domains from aerospace to logistics to software development. The specific technology changes, but the fundamental problems of synchronizing complex operations persist. If this exploration of how artillery tactics rewrote the rules of warfare has intrigued you, consider what happened when another element entered the battlefield equation. Next time, we examine how a different innovation, one that crawled on treads rather than flew through the air, forced yet another revolution in military thinking. The story of how tanks transformed from curious experiment to decisive weapon involves personalities as colorful as the creeping barrage involved mathematicians, and failures as spectacular as its successes. Subscribe to ensure you don't miss that story, and join us as we continue exploring the moments when military technology and tactics collided to reshape history. Riprova Claude può commettere errori. Verifica sempre le risposte con attenzione. Sonner 4.5